on the road. So, in today's most wonderful edition of ENGR 425-R, we are going to be exploring the exciting world of oblique shockwaves. And for this, you will need your book at some point. Right. So just have that available. Last time we talked about we did a bunch of derivations and said, what the crap? All these expressions for oblique shock, for property changes across an oblique shock wave, are pretty much exactly the same as the relationships we had for property changes across a normal shock. It just takes into account the Mach number normal to the shock wave instead of the free stream Mach number. And the flow velocity tangent to the shock wave actually is constant on both sides of the shock, which is like super interesting and intense. So that's kind of where we left off. Did you have any questions on that stuff?
No.
Sweet. So then, before we get started on this, what caused an oblique shock wave? What causes a shock wave?
So, like, what causes a shock wave is something moving super duper fast through viscous medium like air, and once it hits the speed of sound, then whatever, the pressure builds up and then gets small again. But the oblique shock is caused by something that's really pointy.
Okay. Gotcha. As it's called a hole. What happens if it's not pointy?
Then it gets the normal shock wave, nice and round.
So yeah, so there's like a normal shock wave directly in front of it. But what else happens? So like, I can find the video again, the video slide. So like, we're almost there. What the crap's up with this thing? Is that a shockwave?
Like the secondary things coming off of it, or the big thing?
The big thing in front of it.
Oh yeah, definitely shockwave. Definitely.
Yeah.
Good old normal shockwave.
Well, only part of it's a normal shock, though, right? Because a normal shock is normal to the flow, right? So just this guy here is normal to the flow, like right in front of him.
Okay.
The rest of this isn't normal to the flow. So it's called, so it's sort of a trick question. It's both. It's what's called a bow shock. Think of it like the bow wave of a boat.
Okay.
Same thing, just with compressed air.
Mm-hmm.
Sort of. So you're right. This is a blunt body. It's not sharp. It's not pointed. So we don't get an oblique shock, same way we would here. But the flow still has to go around it. So it does that by creating a shock wave. In the front, it ends up being a normal shock. So it's more or less normal to the flow. But everywhere else, it's curved because of how the flow's turning. We kind of intuited last time that there's a relationship between the angle of the shock wave and how much the flow is turning at a given point. Mm-hmm. So we know that shock waves exist to move the flow around a supersonic body. And the angle that the shock wave is at will alter changes with how much the flow is actually turning. But then what the crap's up with this? Because you have an airfoil here, which is a blunt body by definition, pretty much. And there's shock waves on it. But there's no bow shock. So why isn't there a bow shock?
So that would probably be because the free stream flow is subsonic, but as it moves around, it goes across the speed of sound.
Mm-hmm. Absolutely, yeah. So that's transonic flow. So it's high subsonic. Usually somewhere in this, which call usually around like Mach 0.8 or so, but I guess there are exceptions to the rules. So comes over, and while usual subsonic flow increases speed, this increases speed until it goes through the speed of sound, and it decelerates via a shock wave. So that's kind of what we're seeing on that puppy there. And it makes sense that the shock wave is inclined a bit because, I mean, the flow is moving around a curve, so it makes sense that you have kind of a angled shock that turns the flow, not necessarily not necessarily a normal shock. Although in the limit, you can treat it as a normal shock because it ends up being normal to the surface of the airfoil, more or less. So, anyhow, cool. That's awesome. So that's good. That's all good stuff. Let's pop back over to our oblique shocks. So we were here. All right. Cool. And we had said last time, I'm just going to pop my webcam back over to the document camera. So, sweet. The last time we had said that we have our shock wave. We have our flow coming in to the shock. We only care, that's our incoming velocity, our free stream velocity, you might say. Can split that up into components normal to the shock and tangent to the shock. So this would be like Vn1, or let's be like use V1 or V infinity interchangeably there, like Vn1, the tangential one. We also used W for that and U for that. And because we can compute the speed of sound for state 1 for this upstream state, we can compute Mach numbers. So like W1 over A1 is like the Mach number tangent to the shock, and U1 over A1 is like the Mach number normal to the shock. So we said that, and we said, okay, you can say the same thing following. Except that should be angled more. Sorry. It turned. So you can have some Mach number tangent to the shock, some Mach number normal to the shock. Great. All right, so we got there. We said, okay, well, trigs. So we know the wave angle, beta, which is reference to the horizontal. And we kind of take the incoming flow to also be horizontal. We can figure if we know that, we know kind of the turning angle. So this would be like a turning angle. Theta. Betas are wave angle. If we know those, we can do some trig and get kind of our normal Mach number in a pretty straightforward fashion. Hit up some trig, call it a day. By the same token, you can figure out M2 the same way. So we can get so if we get MN1, if I pop back over to my slides for a second here, we have all of these relationships from normal shocks that we can use. And if you look at these oblique shock relations, at least I'm calling them oblique shock relations, you'll note that they're all pretty much exactly the same as the normal shock relations. The only thing that's different is that M1, how everything for normal shocks in terms of the upstream Mach number is now in terms of the upstream Mach number normal to the shock wave. It's the only difference here. So if I can find MN1, I can define everything else. Ba-bam. So popping back over to the document camera, if I have MN1, I know that I can run one of these oblique shock relations. So in this case, okay, I can grab the first one, and I'm just copying it right off of that slide. You can say gamma minus 1 over 2 times MN1 squared all over gamma MN1 squared minus gamma minus 1 over 2. And that's MN2. That's my normal Mach number after the shock. Bam, done. And I just divide that by sine of beta minus theta, and I get my Mach number after the shock. Again, literally, if I can define this, I am set to go. Bam! Look at us rock and roll. So the question is, can I do that? Can I define everything that I'm trying to look for here? So let's have a go at this. Second, I just have to slide these things around so I can look at everything. There we go. All right. So from geometry, I can kind of get these relationships between my upstream velocity, downstream velocities, Mach numbers, and all that. And if I combine that with my continuity equation, I actually can come up with an expression for an expression that relates my wave angle, my Mach numbers, and all that jazz. And it looks something like this. It's somewhat obnoxious. And thankfully, you don't have to worry about this, sort of. So this is what's called the theta beta m relation. Essentially, it's just saying, okay, you have a turning angle theta, you have a wave angle beta, and you have an upstream Mach number, and they're all related to one another. This we know because when we looked at the shock wave in front of the T-38 and in front of the Apollo capsule, or the Mercury capsule, we said, okay, how much the flow has to turn is related to the the angle of the shock wave. Also, the speed that you're going at is also related to the angle of the shock wave. So we know that the turning angle theta, the wave angle beta, and the Mach number of the body moving through the flow, they're all related. And if you work out the math, it ends up being like this, but it's all it's all implicit. So the question is, how the crap do you work with it? The answer is in the back of your book or on the slide. So we pop over to the slide. Here is a excerpt from the theta beta m plot that is in your book. This would be in chapter 9, right in the same area that has all of the other stuff on oblique shocks. Trying to find an exact page for you. Should be around page 610, 613, somewhere around there. This on the slide is the lower half of that chart. So how you use it. So if you look at, if you who just stay on the slide with me for right now, we're going to zoom in a bit on that slide. Let's go to the bottom first. So if you look at the horizontal axis, does everyone kind of see that? That axis?
Mm-hmm.
Great. So that's the deflection angle. That's the turning angle, theta. So that's how far the flow has to turn. If I look at, if I come over to the right-hand side and look at the example of corner flow, you see flow traveling along the horizontal wall, and then it hits a wedge. The angle of that theta of that wedge is your turning angle, or as stated here, your deflection angle. You go to your vertical axis, it says that's your shock wave angle, beta. So that's the angle of the shock wave relative to the horizontal. And then all these curved lines are different Mach numbers, which we see labeled on the far right-hand side. So if you go to the vertical axis on the right-hand side, you see the lowest line is labeled infinity. So that's Mach number of infinity. It goes 20, 10, 8, 6, 5, 4.5, 4, 3.8, 3.6, 3.4, 3.2, 3.0, 2.8, blah, 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 blah. So those are different Mach numbers. So say that I'm traveling at Mach 3 and I have to turn 20 degrees. My question is, what's my angle beta? So find my 20-degree line, I roll up the 20-degree line. I say, okay, there's 20 degrees. Let me just mark that one. About there, I promise. And then there's Mach 3. So I'll go down that line. And where they hit, I can read off, that line, which is my wave angle. All right. So that's called. So that's how to use the chart in a nutshell. So I can come over here and I can say, okay, 30, 31, 32, 33, 34, 35, 37, 38. So my wave angle is 38 degrees for a turning angle of 20 degrees and a Mach number of 3. So this is how we don't have. So this is why we don't have to use that kind of obnoxious equation. We can just read everything that we need off this chart. Now, first of all, does that make sense?
Yeah. So
cool.
what would you normally be given for?
Mm-hmm. Right. So if I'm looking at a problem, what would I usually know? If I say like I'm looking at this geometry here, if I had this sitting still, I could take out a protractor and I can measure this turning angle, right? Because I know that the flow has to follow the contour of the body. So turning angle, it's something that I can measure, something that I usually know. The other thing that I usually know is the free stream velocity, because I'm designing something to operate under particular conditions, right? So therefore, free stream velocity is usually known. Usually, beta is the unknown. However, there are exceptions to that rule. For example, my aerodynamics professor in undergrad, his PhD dissertation was on aeroacoustics. So it was on sound production based on unwanted sound production or vibration based on aerodynamics, specifically looking at the impingement of shock waves created by an airplane on other parts of the airplane, which might not seem like a big deal at first, but there's a story about the X-15, the X-15 being this guy. Wait for it. Okay, screen should be sharing. Can you see my screen?
Yeah.
Okay. The X-15 is this guy. It's a hypersonic airplane made to go around Mach 6 or so. Big, really nice big rocket engine on the back. Be taken up under a B-52, dropped off, and then it would shoot off into more or less low Earth orbit. Kind of intense aircraft. Essentially, just a giant rocket with a guy in the front. However, when it was first made, they had stuck a ramjet underneath the thing, and this thing's traveling like Mach 6, right? So the shock wave coming off of the body of the ramjet, because the flow has to turn around it. Off the body of the wing here, would impact the ramjet and actually would burn a hole in it because of how hot the flow would get around that shock wave. So where shock waves are going is kind of a big deal. So you could also think of this as solving the problem backwards. If we know two things that are going to be in proximity to one another, and we don't want a shock wave generated by one to hit the other, we might say that we know the wave angle, because we know like how steep the wave can be without hitting the other thing. And then we can say, okay, what speed does this limit me to if I don't want to exceed this wave angle? Or how sharp can I make this turn for this wing or whatever, so as to not exceed this wave angle? So you can ask the question a couple of different ways. It all kind of depends on what you're trying to do. But usually, the question is, I have a bunch of measured geometry. I'm evaluating it at a design speed. What's going to happen? Does that make sense?
Yeah.
Cool. All right. So, see if we can do this game. Need to. Okay. So, couple of comments about this plot, though. So if you look at the graph in your book, I know that you cannot read the one that's here worth a darn. If you look at the graph in your book, the thing that's actually, hang on, we can't, you can't read that, but you can read this. Hang on a second. I am suddenly grateful to McGraw-Hill. Okay, so you should be able to see my PDF book. Can you see it? Yes, no, maybe?
Yeah.
Cool, thanks. All right, so here's that same theta beta m chart. Deflection angle, shockwave angle, whole bunch of Mach number lines. You note that as Mach number gets lower and lower, you start to progress into the chart, if you will. Okay, so let's knock down a couple things. One is that if I pick a arbitrary deflection angle, say like 20 degrees, I ride that up, and I'm looking, say, for the shockwave angle following a turn of 20 degrees at Mach 3. Well, I got an answer for Mach 3 down here, right? Down this away. You guys can see that blue box I'm flinging around? Yes, no, maybe?
Yeah.
Cool. But if I go up, go away. If I go up here, there's also a Mach 3 line. And I can find another solution for wave angle way up here. What the crap, right? So here's the gig. There are actually two kinds of oblique shocks that are possible for any turning angle and Mach number. There's a so-called strong shock solution and a weak shock solution. So what kind of wave angle do you think would be associated with a stronger shock? A higher wave angle or a lower wave angle?
The stronger shock, I'm guessing, would be the first one, so that'd be the lower wave angle.
Why? Oh, fair. So it actually ends up being the higher wave angle, but here's why. So we said in a normal shock, the downstream Mach number will always be less than Mach 1, right?
Mm-hmm.
In an oblique shock, can we have a downstream Mach number greater than Mach 1?
Yes.
Yes. So you might think that an oblique shock is quote unquote weaker than a normal shock, because a normal shock will always have a greater effect on the flow. An oblique shock might have a lesser effect. So an oblique shock approaches a normal shock when its shockwave angle approaches 90 degrees, right? So 90 degrees, you're normal to the flow.
Yeah. I was thinking about like the measurement of beta, like the other way around.
Oh, gotcha. Yeah. So the steeper the shock angle, the stronger the shock. So all these dashed lines up here at the top, I know it's a little tricky. I know it's a little tricky to see them, but these dashed lines, those all correspond to the strong shock solution.
Mm-hmm.
So bother. There we go. So everything up here is a strong shock. We're not going to bother with those. We're called because most of the time that an oblique shock happens, it happens as a weak shock. Which called nature seems to have a nature naturally selects what kind of shock is needed. Selects is kind of in air quotes there. It selects what kind of shock is needed to turn the flow, and 9 times out of 10, in the vast majority of the cases that we are interested in, the weak shock case is selected. So we'll stay with these bottom solid lines. All right. Okay. Thing 2. Say that I am flying along at Mach 1.5. So that's like this line here. This guy right in the middle here. Mach 1.5. I try to just call it, and then I throw it into a wedge that's, say, like a 24-degree wedge. So I come out here, I go, what the crap? Mach 1.5 and a 20-degree wedge, those don't intersect. What's going on is not that physics is broken. It's just that everything on this table is for attached shocks, attached oblique shocks. So if I exceed if I look at, say, Mach 1.5, it has a maximum turning angle of about 12 degrees. So that's the maximum that a flow going at Mach 1.5 can turn around a corner and still have an attached shock. That's what's called a critical angle or a maximum turning angle. Let's write that down somewhere. So that's the maximum angle for an attached shock wave at a particular Mach number. That's just something that we're going to have to keep in mind. All right. Excuse me. I think that's everything for this plot. Let's just work through a couple exercises with it and see where things go. All right. Any questions before we leave this?
Nope.
Great. Note that there is a second page of it, so don't miss that. All right. That's on page 626 of your book. Unless you got an older one like I have. All right, so let's jump back to the document camera and get it on. So just kind of wrote out that chart a little bit. Okay, so let's look at an example. So say that I have a wedge. I'm moving through the flow, and if I try to define that wedge, theta in this case, which we said is how far the flow is turning, which it is, because right, I have my flow coming in here, then it has to follow the contour of the body there. That turning angle is also called the wedge half angle. So, question is, I have an incoming supersonic flow. It's what's called. Let's just say it's coming in at Mach 2. It has to turn 20 degrees. What's my wave? What's my wave angle? So I can go to my chart. Say can get a piece of paper for a straight edge because that's going to be super useful. Find where theta equals 20 on the bottom. Find the Mach number 2 line, and then go over to my beta, and I get a number of 4. I get a beta of about 53 53 degrees. You guys all get that?
20 degrees from 2. Yeah, that's what I got. 53.
Cool. Now let's take that same example. But instead of an incoming flow of Mach 2, let's crank that up to Mach 5. What's our beta now?
Mach 5. Oh boy, that's on the other page, isn't it?
Nah, you just scroll down a little bit.
Mm-hmm. Mach 5 degrees. Oh boy.
What do you got?
Like 28, 29 degrees for beta.
That sounds good to me. All right, I got about 29. Okay, so we can see that as we crank up Mach number, the wave angle goes down, which, if we go back to the slides, if we go way back when we looked at shock waves around a bullet, that actually matches with our observations there, because if you look at the bullet with the shock wave in front of it, Mach 1.04, is a kind of just barely inclined detached shock. As we increase even in 3/10 of a Mach number, that shock wave really starts to incline and sharpen up. So as you crank up the Mach number, we can expect the shock wave angle to kind of get to kind of steepen up for a given deflection angle. At the same time, what if we cranked up the angle theta? So at Mach 5, deflection angle was 20. Let's crank it up to like 32. What's our shock wave angle now?
Or 20 degrees theta.
Yeah, we'll crank it up to a deflection angle of 32 degrees.
And we're still using Mach 5?
You got it.
44 degrees?
Yeah, so our wave angle was 29 degrees. So by cranking up the deflection angle, we also cranked up the wave angle too, which kind of makes sense, right? Like if we have what you call, like, if the body itself is further out, it makes sense that the wave kind of follows with it, right?
Mm-hmm.
So it's just a couple of things when we start looking at how different properties vary with respect to one another.
So I have
Great.
a question.
Yeah.
So, like, with the picture, the shadow photography picture of the I don't know which plane it was, but one of the fighter jet planes.
Here, let me run back to it quick. Yeah.
So, could you, like, figure out what the beta angle is there, and then figure out what the turning angle would be?
Yeah. So if I could measure this wave angle from the picture, I could figure out how far the flow is turning to, like, go up the nose here. The only caveat to that is we're considering everything in 2D right now,
Uh-huh.
and the nose of that plane is a 3D artifact. And we've said that 3D stuff varies from 2D because you can get flow interactions around it, and supersonic flow is no exception to that rule. So there will be some small differences, but yeah, you totally could. Yeah.
Okie dokie.
Yeah. I think that I'm trying to remember. It's in your book, but I think that the wave angle for cones, so a 3D object, as opposed to a 2D wedge, I think that the wave angle ends up being shallower, like lower, because because the flow is a place to go. Essentially, that's what you call it. It doesn't have to distribute itself along the flat of a wedge. I think that's true, but I'd have to look at it.
I believe you.
Oh, thank you, thank you. So that's the basics for an oblique shock and an attached oblique shock. So given some geometry, we can find the wave angle. If we know the wave angle and the geometry of the free stream conditions, we can find pressure variations, density variations, temperature variations, whatever. We can find whatever we want across that shock wave. So, what if we have a supersonic airfoil? Can we find lift and drag? So, let's have a look. So, popping back over to the to the document camera. So, your typical supersonic airfoil is a sharp pointy thing. It's not at all like a subsonic airfoil. This is why you don't see that many of them around, because all planes have to fly at subsonic speeds, and these things suck at subsonic speeds. So the planes that have these only travel fast, like the X-15. Its wing is essentially a plate, a flat plate. There's your usual supersonic airfoil. It's just a big old diamond. Let's just consider the front half here, though. So there's a wedge. I'm going to say that this wedge, the half angle theta, theta being 15 degrees. It's at an angle of attack of 0. So my flow is coming straight into the wedge. We'll say that Mach 1, that Mach in state 1 is 5. Mach number in state 1 is 5. We'll assume that the ambient conditions in state 1 are sea level standard. So that means the upstream pressure is 1 atmosphere, densities 1.225 kilograms per meter cubed, blah, 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 blah. Temperature is 288.13 Kelvin. Let's also assume for a second, it's probably the biggest assumption that we're making, that the pressure on the back end of the wedge is atmospheric pressure. It's a really big wedge, really big wedge. We know that because the upstream Mach number is greater than 1, we're going to have a shock wave here. We're going to assume that it's an attached shock coming off the nose of that wedge. So we're going to have, so that's because it's going to create a shock wave. We're going to have flow after the shock wave, some Mach number, pressure, blah, 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 blah. How do I get lift and drag for something like this? What are lift and drag?
Forces that go up and backwards.
Okay. So if I can find forces, I can find lift and drag then, right? So okay, let's run with this. Say that these upper and lower surfaces, let's say they have a length L.
Mm-hmm.
How would I, let's call it, assuming that I know P1 and P2, how would I find drag, say? And remember, this is 2D. So we can ignore depth, if you will. You can ignore how far into or out of the page this wedge goes, because it's 2D.
I want to say, like, due to the viscosity of the air, that'd be creating a force on it.
Okay, good. You're absolutely right. However, what has our assumption about viscosity been throughout our derivation of compressible flow relations?
Throwing everything out the window.
Yeah, we've been saying inviscid, adiabatic, reversible, compressible flow. That's what we are looking at. So there's no viscosity here. There's no viscosity. Again, I'm kind of hand-waving things a little bit. The relationships still work, but this is kind of what you're looking at are kind of the forces that we got. So how do I get drag? I know it's a little bit of a drag.
Mm-hmm.
How do I get it? You said before that it's a force balance, right?
Mm-hmm.
Can I get forces from the pressure that's acting on the body?
Yeah. So I guess would the drag have to be equal to the pressure that's acting on the back?
Not just on the back,
And on the front.
And on the front, right? It's the net force in the horizontal direction. That's drag. So You might think of if I did a summation of forces in the x direction, it'd be like P, which is called P1 here, times the area associated with that, minus, if you will, I guess that's going forward. So that's my positive drag direction. That's my drag direction, and I'll just call those my positive directions for now, just so I have something to reference. Plus the horizontal component of the pressure of the force generated by P2, right? It's like P2 times A front times what? Cosine of 15 degrees?
Yeah, cosine.
It's going like this. Actually, it looks like it'd be sine. It's like, because the pressure's acting like that, right? Normal to the surface.
Mm-hmm.
So if I'm trying to find the horizontal component of that, 15 degrees would be there. That guy there, so it'd be sine of 15. Then plus drag equals 0. So that'd be like my summation of forces. Oh, and do I just have to account for one of these sides or both of them?
Both of them.
Right, and that's just for one side, so I have to multiply that by 2.
Mm-hmm.
So if I solve that puppy out, I get my expression of drag. So if I rewrite that up here, solve for drag, like drag equals 2 P2 A front sine theta, or sine 15 degrees. That's a minus. Yeah, it's a minus. Yeah. Right?
Wouldn't that be?
Wait, hang on. My sides are. Yeah. Yes. Oh yeah, that's a plus. Definitely a plus, right?
Mm-hmm.
Am I screwing this up?
Well, what I think your sign convention was that those forces were in the positive direction.
Yeah, I think you're right. So I'll call it. So that'll be a negative there, plus a P1 A rear. Yeah. If I subtract it over to the other side, everything gets flipped for some reason. It's kind of odd. Oh, it's because of that. Okay, cool. I'm on board. What's happening now? All right. So we know that our drag is just the difference in force acting on the front versus the force acting on the back. There we go. Fold this guy down a little bit. There we go. So we know that's true. That's intuitive. We also know that we're looking at a 2D wedge. So instead of looking at areas, we're really looking at lengths. So L is the length of that guy there, or if you want to be snazzy about it, that, well, the length of each of those lines is L, is length L. So P2L sine theta. P1, how do I find the length of the back end of this thing?
That would be the sine of theta times the length of it.
Yeah, so L sine theta is that guy there. So 2L sine theta is the top and bottom. I'm half of that side. So wait. So there we go. And if I pull everything out, you get something that looks an awful lot like this. 2L sine theta. I still think I screwed up the sign somewhere. Definitely I screwed up the sign somewhere. Definitely screwed up the sign somewhere. No, I did. Hang on. Got to figure this out. I know the signs are wrong. I know the signs are wrong.
Well, do we normally consider drag to be a negative force?
It does. It doesn't matter if I flipped my sign convention. Go that way. Positive, negative, negative. I know my signs are wrong. Oh, you know what? Bet I'm thinking it in the wrong way. I bet I'm thinking this way. I'd say that's traveling in the opposite direction. No. Oh, yeah. I know exactly what I'm doing wrong. Drag's on the wrong side. So the summation of forces is pressure force from the back. It's a balance between the pressure force on the back, call that negative for kicks and giggles, pressure force in the front, and the difference between those is drag. The difference between those is the resultant motion of the vehicle, or MA, or drag.
Mm-hmm.
That's what's throwing me off. So now the signs all work. This is positive. That's negative. Life is good and it makes sense. And this comes out to P2 minus P1. Awesome. All right. So we get this. This is a statement of what drag, of how you can find drag. So we just need to find P2, really? Because P1, we know it's the sea level standard air pressure. So how do we get P2?
Our equations of before and after shock waves.
Woo! Sounds awesome to me. So how do we use them? We got Mach 1 is 5. Can I just plug that into our expression?
I think so.
Right, it's called. Do I use the free stream Mach number or a normal Mach number?
I think we can just use the free stream Mach number.
I think you are incorrect. Right, sorry. Remember, remember, an oblique shock wave acts like a normal shock wave, but only to the flow traveling normal to it.
Mm-hmm.
So we need to find the component of that flow traveling normal to the shock wave. In order to find that, we need to find the wave angle. So how do we find the wave angle?
Awesome chart.
What?
With our awesome chart, right?
Woo! The awesome sauce chart. So I can go down to my chart, find a deflection angle of 15 degrees.
Oh man, that's a shame. Why are these steps of 4?
Yeah, keep in mind that on the bottom, every 2 lines is 1 degree. So it's in increments of half a degree on the horizontal axis. So I can look at that, take it up to Mach 5, run it over. What do you get?
$23?
Yeah, I got 20. I got 24. Let's cut the difference and call it 23 and a half.
All right.
So I got 23 and a half degrees. Said the normal Mach number is what? The free stream Mach number times sine beta.
Yep.
That gets us a normal Mach number of roughly Mach 2. Or 1.994.
Very precise.
Woo! Hey, if you don't have at least 3 sig figs in there, hurry, you need to look at it again. So, if we got that, we can look back to our oblique shock relations, which we said were pretty much exactly the same as the normal shock relations, just with the normal Mach number. So 1 plus 2 gamma over gamma plus 1 times quantity, the normal Mach number squared minus 1. That's P2 over P1. So I can run over here and say P2 over P1, 1 plus 2 gamma over gamma plus 1, normal Mach number squared minus 1. So if I solve that for P2, I'm just multiplying everything by P1, really. And that gets me what?
So what did we say the
Specific heat ratio?
so
Gamma?
I got 4.47.
Same here. Sweet. So 4.47 is the result of all this stuff, right?
Mm-hmm.
And that equals P2 over P1.
Mm-hmm.
P1 is what again?
P1 is 1 atom.
Yep. So that means that P2 is?
4.47 atoms.
You got it. So P2, 4.47 atmospheres, or some ridiculous number of pascals. If I multiply that by a hard 1,325. So I got my upstream pressure and I got my downstream pressure. I do have to put those into pascals, else my units of drag are wonky, because who knows what the crap an atmosphere meter is or whatever.
Exactly
So
100,000.
What?
I don't know.
Okay, good. If you did, I was going to get scared for a minute there. So if we say that our wedge is 1 meter long, that means that I can just recopy my equation quick. So and P2 is 4.47 atmospheres, or 4.47 atmospheres is the same thing as 453,000, your 9.6 pascals. P1 is 1 atmosphere, or 101,325 pascals. Your drag is 2 times that L is 1 meter, sine 15 degrees. It's a turning angle. P2 minus P1 is 351,684.6 pascals. That gets us what? Drag is 182,045.4 newtons per meter of span. Because remember, this is a 2D object, so this is like a 2D drag. It's newtons per meter of span. But that's drag. I want to find a drag coefficient. How do I get drag coefficient from drag? What's the relationship there?
Wow. Oldies but goodies there.
Yeah.
CD equals drag divided by a whole bunch of stuff.
Yeah.
So if you divide that by 1/2 rho v squared.
Yeah. And because it's 2D, you also divide by the chord length.
Ah.
Yeah. So Q infinity is your dynamic pressure, that 1/2 rho v squared. See, it's the free stream density, the free stream velocity, and the chord length. So we know the free stream density because we said that everything's sea level standards. That means our density is what?
1.225 kilograms per cubic meter.
Sweet. Our velocity, well, we know that a free stream Mach number is 5. How do I get a velocity out of that?
Well, since it's sea level standard, the speed of sound is 343 meters per second.
Right. Or if I wanted to compute it, I could say square root of gamma RT, right?
Mm-hmm. Or a bunch of other things.
Yeah, but this is one straightforward. I know that T is 38.13 Kelvin.
Mm-hmm.
So I can do some quick math with that and say 288.13, 1.4, 287, multiply them all together, take a square root, and that gives me 340.25 meters per second. Multiply that by 5. Gets me a speed of, so that gets me a free stream velocity of 1,701.3 meters per second.
Mm-hmm.
My chord length then is all that I have left. And how do I find that?
That's the cosine of 15 degrees times 1.
Yep. So look at my geometry. I say, well, 1 meter times cosine of my wedge half angle. Get that. So 15 cosine. So that's like 0.966 meters. So I take my number for drag, divide by 1/2 rho v squared times c. And that gets me something that looks an awful lot like this. Um, 182.045.4 called 5. Oops. 182.045.4. And that gets me a drag coefficient, a 2D drag coefficient of 0.106.
That's what I got.
Awesome. Now, wait a second. This is a viscid flow, right?
Mm-hmm.
Could we ever get drag coefficients for an viscid flow that weren't associated with lift?
Sometimes.
No, we never could. We only could find induced drag or drag due to lift. Is this wedge? Should we be expecting this to make any sort of lift here?
No, it's symmetrical.
It's symmetrical. Angle attack is 0. Everything's telling us this shouldn't make any lift. So induced drag should be 0. What the crap's going on here? But really, it's kind of a trick question. Is our flow completely inviscid?
Nope.
Correct. We have that shockwave thing in the middle, which is a viscous phenomenon. So we kind of violate the premise of D'Alembert's paradox. So therefore, we're not bound by it. So shock waves produce drag. It's usually called wave drag because it's made by a shock wave. So this is a form of drag called wave drag. It is not associated with lift. It's not parasitic drag per se, because it is specifically associated with the fact that there's a shock wave in front of the body. If the shock wave wasn't there, you wouldn't be doing all this math to get what we just did. So that's that. Any questions there?
Nope.
All right. Well, in that case, that's about all that I got for today. I did want to give you guys one more test grade, just add something else in that category before the final. Might also be a nice check-in review kind of thing. I was looking at the 21st for that. Does that sound good? It's like 2 weeks from today.
Okay.
So next week, let's plan on doing a little bit of review on the 16th. 16th. Yeah, let's do review on the 16th. So if you have any questions that you want answered, get them together for the 16th, and we'll go through them. All right.
Yeah.
The test will include pretty much everything that we've done up until today. Anything up until today from where we left off last time. So I think with 2D aero from 3D aero to here is all fair game. 3D aerodynamics to now. All right.
Okie dokie.
All right. Thanks for stopping by, y'all.